the main object that we were looking for. Field integral representation for the partition function. At the end of the lecture, I will just point out that this, of course, I mean, from the partition function, you can calculate all thermodynamic quantities, but this can be also used as a generating functional by introducing some kind of sources for imaginary time-ordered correlation functions. And so now, I mean, we do it in reverse, so we will discuss examples. So there's a systematic way to show how these imaginary time-ordered correlation functions are related to the typical correlation function that one is interested, let's say, in transport measurements. And this is by so-called Riemann representation. And so probably we won't discuss this now in this lecture in detail. Maybe make some exercise, or who's interested, I mean, we can discuss this then. But the idea is really then to put this to work, to look at some examples and not go too much into details. I would just mention at the end of this lecture, like, how to generalize this object to a generating functional for imaginary time-ordered correlation function. You should believe me, then this is like of interest for typical correlation function. So this is partition function integral, now not over all paths, but over all field configurations in imaginary time from 0 to beta. And each field configuration is weighted by some say statistical weight, which corresponds to the action given here. So we have typical forms, this time derivative, Hamiltonian, and since we have the canonical partition function here is the number operators, and then importantly we have the boundary conditions which are periodic for bosons and antiperiodic for fermions. So I'll just write it once more down in a more explicit form. The action for the prototype of Hamiltonian that we were considering is then given by an integral. Now the indices ij, which will be probably all our applications just to d-dimensional space. So it's a continuous variable. Then we can write this as contribution, which is diagonal in this Hilbert space index ij. Time derivative in terms of potential, and then we have the Hamilton matrix element of this tau, and then we have here the interaction term, which is psi I tau, psi R0 tau, so they are all at the same time. All local in time. Oh, and I forgot here the matrix element okay, so that's the object that we are interested in. Now there's another representation of this function integral, which is actually the one that we will use in, I think, most calculations. And this is just using that, well, here we have a differential operator, which is a time operator, and it's more convenient. So in the end, if we look at the function integral, we will encounter many like determinants or inverse matrix element of this operator here. So it's convenient to change to a representation in which this operator is just diagonal. Okay? So it's to change to a representation which diagonalizes this operator. So in the first step, these fields all are imaginary time dependent. So let's change to the corresponding Fourier representation, which again diagonalizes time derivative. They are like in the harmonic oscillator. So this has the advantage that then we have here numbers, and this is the so-called Matsubara representation. So this is one that's frequently used, Matsubara frequency representation. where I said the idea is to change to a representation which diagonalizes the time derivative, and we have to be careful with the boundary conditions. So let's observe that psi tau and psi bar of tau obey periodic or anti-periodic boundary conditions for bosons specifically for fermions. And this can be used to, instead of using an imaginary time representation, to change to the Fourier. Fourier representation. Use the Fourier series, Fourier representation in the usual way. Where we write psi of tau. Now, this here normalization factor, 1 over beta for convenience. Then we write this as a sum over frequencies. And what we sum is the coefficient of the field, and then exponential, and the inverse is given by the inverse Fourier transform, we integrate theta and tau, c of tau by omega and tau. So this is just a conventional Fourier transform. Now we have to be careful that while we have the usual periodic boundary conditions for the bosons, we have the anti-periodic boundary conditions for the fermions, and this means that we have to take different frequencies. These are the so-called Matsubara frequencies. So omega n should be a multiple of 2 pi versus the temperature. So let's write 2n pi t for bosons, where n is just an integer, but it should be the odd integer for the fermions to account for the anti-periodic boundary conditions, okay? Where the n in both cases is an integer number. Okay, so we have to take into account, well, if we take here the even integers, well then we see that this is periodic, but the odd even, due to the additional factor I pi, we get here the anti-periodic boundary conditions that are needed. Okay, so these are the Matsubara's frequencies, the bosonic and the fermionic Matsubara frequencies. So this will be most times our starting point when we do the actual calculation. And see, so now what do I want to use? What do I want to use? Did you copy this, or maybe I can wipe away this? So is this idea clear? So we just, these are eigenfunctions of the differential operator. Okay, so that's why we use the frequency representation, but we have to be careful due to the boundary condition to account for the right frequencies. Okay. So I can raise this here. So let's then write down the corresponding representation of the partition function, the Matsubara frequency representation. So do you know these, or is this new for you, or already heard about them, but never did calculation? Because in the end, what one has to do is a lot of like sums over functions which depend on these Matsubara frequencies, and there are some techniques, and probably you don't know these, or okay, then I know what we have to do. So what we will see is that actually this, so again, I mean, this, all the physics is encoded here, so we will see that due to of these different Matsubara frequencies, then once you do calculations of some correlation functions, which will be expressed as functions over these frequencies, due to these properties, there will naturally appear then bosonic or fermionic distribution function, both of the fermionic distribution function. So there's what in here, which we will then discuss. But first, let's write down function integral Matsubara frequency representation, well, which is just using the Fourier transform, but still I want to write how it's down because there's some like small subtleties and whatever that I just want to mention. So we can write it down again as an integral over field configurations, where now the measure is that over the product of the fields in whose n here is the Matsubara index, okay? And the action itself now is the Fourier transform okay, so this is just again the measure, and there's some, yeah, okay, I mentioned this, there's some detail here that I just mentioned still, but this is just writing, well, this measure here, which was before like the product of the discretized times, now it's the product of the frequencies, and actually this is something that we already discussed in the harmonic oscillator. No? So now the action is the Fourier transform of this, so the derivative becomes just the number, and then this is diagonal in the Matsubara frequencies, so let's write this down. This is the sum over frequencies ij minus I omega n minus 2 ij. So this is a good exercise to do the Fourier transform. Now if you take all the factors beta right into account, get here a sum over n1, n2, n3, and 4, so fourfold summation. Matsubara frequencies, then ij k down, matrix element, okay. L. Sine bar I and 1 sine bar j and 2 sine j and 3 sine L and 4, and then we have a delta function which sets the sum of the Matsubaras to 0, but I should have here the minus. Okay, so this is a good check that you should once just do the Fourier transform of this.
That 4 fields there shouldn't be 1 over beta squared. Because for each beta you have 1 over.
Yes, but then you have to be careful with the delta function here. So if you look at, so let's first look at this one here. So you insert this one here, then the d tau integral will set your both metrics. So you would, for example, here you set in c bar n and cn prime. Okay, then you have a function 0 to beta d tau e to the I Yeah, omega n minus omega n prime tau, and this will give you a delta function. But you have to be careful with the betas. So what we use heavily here is that this here gives you a delta function in n, but actually with a beta. Okay? You just see when n is 0, you get a beta. Okay? And this is the same reason why you get a 1 over beta here. And this delta function then just erases from, well, you have an I to the omega n1 plus omega n2 minus omega n3 minus omega n4, all is local in time, so you have the integral over d tau. This will be your beta times the delta function. Now, just very briefly, well, what does this tell you? Like, this is the time representation, this is all local in time. So this is a two-particle operator, local in time. This just becomes diagonal in the energy, okay? So this is, let's say, energy conserving. Now here you have a four field operator for Fermi for boson operator, which is also all local in time. And this translates to some operator, it's a function which is now in the field, which depend on different energies, but you have overall energy conservation. Okay? Just reflecting the structure. Okay? So this is like energy conservation here.
I'm not understanding the first term, the sun, that sun.
This here?
No.
Or?
The first minus.
Oh, minus I omega n.
Okay.
So that's the frequency. Okay, that's really bad. But it's just, I mean, using that this are Einstein functions of the delta tau. Okay, so let's just remark some subtleties and some maybe I do some exercise too, but maybe it's also too much detail. But let's see, what did we mention first? So let's look at this expression here. Here we have a time integral and a time derivative. So h bar is always actually set 1 here now. Okay, I didn't mention, but h bar in kb is also. So this is all dimensionless here. No, that's fine dimensional. So the fields here are dimensionless. Okay. Now here you have actually dimensional sums and an energy. So these size should carry the units of 1 over square root energy. And this you can also see from the definition of, okay, I wiped it away, but it was 1 over square root beta. No? So this means that one has here to be a little bit careful with once you do Gaussian integrals, and I just mentioned this as a remark. One typically doesn't have to think about these kind of issues because, I mean, there's normalization things which normally do not lead to problems, but whenever you see you arrive at some result, like start out from Matsubara representation, arrive at a result which just unit-wise doesn't make sense because units turned out wrong. It's good to recall the following, that the integration measure in Matsubara is the following. So the integration measure in Matsubara frequency representation. Actually, you have to be careful with this with the units, so there should be some factor which compensates this. So just write down, so the field psi n with psi bar n carry dimension energy to the 1 is minus 1/2, and that is that if you make, for example, a typical Gaussian integral that we it's the kind of integrals that we will do a lot. So once you Matsubara. Coherent state, integral, Gaussian type. Coherent state, integral, normalized follows. So if you have here the integral over psi n, which are now the Matsubaras, and you have some typical Gaussian integral, which has here some energy. So this is all dimensionless because this product here is 1 over energy. Well, still you should get something dimensionless in the end, okay, because you started out. So there must be some energy compensating factor in the measure, okay, and this is just 1 over temperature, okay. This is just, you have to be careful. So if something dimensionally wrong comes out, you should recall that if you go to the Matsubara representation, there's still some factor in the measure which gives you then the right units when you do the Gaussian integral. Well, this is, I mean, you normally don't have to care too much about it, but if there's something wrong happening, it's good to recall this. And the second one is also something very subtle, which is good to know only if there's again something strange appearing. And this is another remark which is on the construction subtleties. And I think that's in general like a good strategy. I mean, don't think too much about small details. Whenever the calculation that they do make sense, if there's something weird happening, then you should go back and look at some things that can go wrong. So what we used in the construction was that we substituted, so this was the time slice, this by some local terms. And then we did change to the Matsubara representation, let's say, of this quadratic non-impacting term, this term, then by construction into something local in Matsubara space. Okay? So same index here. In Matsubara representation. So the same actually for the particle number. So so there we had omega n sum of I psi bar I n minus the psi I n. So again, what we did is also for the particle, what we did, we started out from a number where the fields were shifted by one time slice. We approximated this by some diagonal because we said, well, should be fine. Then did the Fourier transform, which turned this into some local quantity. Okay, same evaluated at the same frequency. If we would do all this more accurately, instead of first like going to time and then change back to Matsubara, if we would just use here everything more accurately, taking into account that this corresponds to a slightly shifted time slice. Well, we know what this means. The time slice shift is just the exponential of a small, like, the mismatch here can be absorbed into some frequency mismatch, no? Like factor into the I epsilon n tau, okay? Not epsilon n, but one like distance between the Matsubara frequencies, okay? So if we would take this expression here and do the Fourier transform to Matsubara frequency, you would not get the delta, okay? Like, we had something like this, psi tau tau, here integral over tau. Now we inserted here psi n and here psi n prime, and then we had the integral over e tau, e to the I n epsilon minus epsilon n prime tau. And this gave us delta, which said these to be equal. Now if you would take into account this small time shift here, this wouldn't be epsilon, this would be the same, set to the same epsilon, but to one shifted. Okay? So what you would actually get, let me write it down, so you can check this. If you would do this more accurately, keeping the small mismatch in time-wise, what you would find for the Hamiltonian would be sum over omega n, sum over ij, and then psi bar in, and there would be e to the I epsilon n delta hij psi. And for the number operator, you would get omega n sum over I psi bar in minus e to the I epsilon n delta psi n. Okay, so this would be just due to this one step here. Okay. Now, normally you don't have to care too much about this factor because in the end we send delta to 0. This is why we didn't mention that. There is some very rare cases where actually you get some terms once you write down, let's say, start out from the Matsubara frequency representation in the normal form, where we won't care about this, and you want to calculate some correlation function. You see that this correlation function will typically be some sum over Matsubara frequencies, and you just see that this sum is not convergent. It's actually, I think, one example that I know, maybe make an exercise. So you see that this is not convergent, and in this step you should recall, oh, well, there was some subtlety that I didn't care about, and there's a very small factor which then, if you go back and take this into account and include this into the correlation function, you'll see that actually this factor will make everything well behaved and convergent. Okay, so I think we'll make an exercise for this. Okay, so again, the idea here is, well, don't care too much about these kind of details. You might run at some point into a problem that you arrive at some correlation function expresses some of Matsubara frequencies, and we still have to discuss how to do this. Where to find something that is divergent, then it's good to recall, oh well, I recall that there was set some time, well, we made some approximation, we weren't completely accurate because normally it works, but it might be one of the rare cases where this will then be the reason why you found something divergent and where this will solve the problem. Okay? So we make an exercise for this. So that was the second comment. And then just the last comment, and then we stop, is just on what I said in the beginning. So what we're talking here about is a field integral representation for the partition function, but we can generalize these objects in the following way. Or questions? So I think it's good, to do once this year, it's just fully transform, but it's a good exercise, and get back to this field.
Where should this problem occur? So like in some high speed, in some high frequency?
So when you, for example, calculate the simple thing like the Green's function for the harmonic oscillator, so this has to do with the correlation function that might want to calculate some expectation value. This here now corresponds to an expectation value, which is defined as sine to the minus psi. So you have the statistical weight. You put here the operator, then divide by 0. So this is the expectation value. So if you want to calculate this at equals time, so where tau also goes to 0, this should give you something like the occupation number. There you exactly find the problem. So you get some, we'll come to this, but this gives you like, it's kind of Gaussian integral, so this gives you 1 over the inverse operator. So the operator here is like an I omega n, and then let's see, say just a harmonic oscillator, you have just one frequency, so omega 0. And if this is equal times, you will have still the sum over all n. Okay, so you see that this is like, looks divergent. But this factor will heal it. So it's a 1 over n, and you know 1 over n is divergent, but if you have 1 over n with some oscillating function, this is, makes it convergent. Okay, so this is the one example. And I think I explained this here really bad because in the end it's really I'm just putting in 1 here is the 1 delta. Okay, so let's make a comment on imaginary time ordered or imaginary time generated. And again, one can make this more formal, but I guess we won't do this in this lecture. Because like for the applications we discuss, this will not be too interesting to spend too much time for here, but I'll just manage it. So the outlook is that the finite temperature correlation functions that one is typically interested in for, let's say, calculation of observables can be found from imaginary time-ordered correlation functions by some analytical calculations, and the imaginary time-ordered correlation functions are readily calculated from generation of this. So what I mean here, okay, let me just write down this first. Finite temperature correlation functions are found from imaginary time ordered correlation functions by something that we already counted, maybe by analytical continuation. And one can make this all very formal if one wishes, but just try to motivate it. So the idea is that, like, what we are typically interested in, like, that you make some small perturbation to the system and you want to calculate or find the response. Yeah, you apply some small magnetic field or small electric field or whatever, you want to see the response, like in form of a current. So the typical functions, correlation function that we calculate on the spanner first is like the linear response correlation function. You make a small perturbation and see what linear response you get, like twice small field, and see what is the current which is linear in the perturbation that you do. So the function that will appear should be functions, correlation function at finite temperatures. So what you typically want to know is, like, you apply at some time, let's say 0, a field, and you want to see what is the current that flows through the system at time t, and all this at finite temperature. And these are then the typical, like, the retarded or advanced correlation functions, because I mean you have to respect, typically the retarded, you have to respect causality, that well, the signal should come after applying the perturbation. And these are then retarded correlation functions at finite temperatures. And these functions can be nicely generated from imaginary time-ordered correlation functions, which are the following, which are, let's write down already, like an endpoint correlation function. say this is a function that depends on n components and times tau n 1 to tau n to tau n, tau 1 to tau n, which is just the expectation value of this is imaginary time ordering operator of such correlation functions where the creation operator and annihilation operators acting on at different times. Okay? And this here is the expectation value with respect to the action in the imaginary time. Okay? So these would be like imaginary time ordering operator. This is expectation value of creation annihilation operator. Now, if you would start out from something like this and now do the construction of the function integral that we did, all that would happen is that these times you can easily, like these operators at specific times, you can easily incorporate into the function integral if you put them at the right moment where you insert the resolution of unity. Okay? So these, if you do this, then they will just become the eigenvalues of the corresponding operator at the corresponding time slice. Okay, so this will then become just a field variable evaluated at specific times. So if you express these in the function integral, this will be expectation values with respect to this weight. Okay, the weight function would be this here and then divided by z. So this would just be already brought down side by side, it's nice outside. And then right here the operator in terms of the eigenvalues, and we divide this by normalization. So these imaginary time correlation functions will be typically then here in this form like products of these fields at different times. Now these functions you can readily generate if you introduce some source term here. Okay, so introduce some source. Let's say you change S to S plus Sj, where Sj is external form is written with okay, so this is now then depending, this would then be a z that depends now on all these variables j1 to jn. Okay? And now you can, starting out from the log of ln jg, you can now, by derivative with respect to the sources, you exactly generate these correlation functions. You get the 1 over z, and then this expression here, and taking the derivative with respect to j1 at tau prime, you get exactly like this function here. Okay, so this is just a brief remark, and we'll see how we come back to this, but not in the very formal way. But let's keep this in mind. We can generalize this by adding some source term, which then allows us to calculate imaginary time order correlation functions. And these are, in some sense, that can be made very precise, related to the typical correlation functions, finite time retarded with one correlation function that we are interested in if we want to calculate the response to some extent. Okay, this is just an outlook, and we don't go too much in this direction now, but we go to the application.